Welcome, ladies and gentlemen. So as we go backwards and evaluate indefinite integrals, please note that's the same as finding an antiderivative. So in order to go backwards and evaluate an indefinite integral, we're finding an antiderivative. That is a function that when differentiated will produce the original integrand there. And so we're looking for a function that when differentiated produces cosine of x plus root x. And so we've got a couple different things to help us. One, we know our trig derivative rules. We also know our power rule for differentiation, so we can reason out a power rule for anti-differentiation by reversing our differentiation process. Let's go ahead and go term by term. So if we have a sum or difference in a function, we can differentiate that sum or difference by going term by term. So too then can we anti-differentiate, that is, evaluate indefinite integral by going term by term. So we'll just break this up and go one at a time. For an antiderivative function, what differentiates to cosine of x? Well, sine of x differentiates to cosine of x. And do we need to include a negative? No, the derivative of sine of x is cosine of x straight up, so that's no problem. A little bit trickier would be an antiderivative for the square root of x. And so up in my original, I will think of this as x to the 1/2. And that way I can find an antiderivative by undoing my power rule. The power rule for derivatives is the exponent times the base raised to 1 less. We're going to undo that process. And so the first thing we're going to do is add 1 to the exponent and then divide by the new exponent. So here we go. Add 1 to the current exponent. That would be x to the 1/2 plus 1 is 3/2. And then divide by the new exponent. The new exponent is 3/2, so dividing by 3/2 is the same as multiplying by 2/3. And so an antiderivative for x to the 1/2 should be 2/3 x to the 3/2. And then because we're finding an indefinite integral, right, we could have had some constant added here, tacked on to the end that we don't know about, so we must include that as a plus c. That's called my constant of integration. So an antiderivative for the first function would be sine of x plus 2/3 x to the 3/2 plus c. Raise your hand if you have that already. So who had that for number 1 already? Good job, you guys. And so we've got our straight and differentiation, no problem. Again, break it up and go term by term. I think this one will go straight as well. Go ahead and share yours with the class, then we're ready to share number 2. I know you guys can do that term by term. So what did you get for number 2, Allie?
2e to the x plus 3/4 x plus negative tangent x plus c.
Nice job with the signs here, Allie. So we've got 2e to the x, that constant multiplier sticks around, and then e to the x differentiates to itself, so too must it integrate to itself. So 2e to the 2x, integrating with respect to x, right, gets us back to 3/4 x, and then tangent differentiates to secant squared. Therefore, negative tangent of x must differentiate to negative secant squared. Nice job with signs. Don't neglect to include your constant integration. Raise your hand if you have the same as Allie. That's correct. Way to go, you guys. All right. Now, what gets tricky? Well, what gets tricky is when it's not one of our straight derivative rules from the symbolic form, but when we have the chain rule involved. And then we have to account for the fact that my inner function here has a derivative itself, right? Sometimes that constant is or isn't present. Sometimes we need to provide for it. And so as I look at this first part, squiggle, underline, secant 3x, tangent 3x, as I look at that first part, I know a derivative rule that produces secant tangent, right? What differentiates to secant x, tangent x? Sophia? Yeah, secant of x. But this isn't secant of x, it's secant of 3x, an inner function. And so if I had an antiderivative function that was, secant, I know that that would differentiate to a secant of angle times tangent of angle. I also know that my derivative words for a trig function keeps the angle. And so that angle in my integrand 3x must have been the angle in my original function. So this must still be 3x. Because the derivative of the trig function is the derivative of the trig function with the angle, and then times the derivative of the angle. Because I have an inner function here, 3x, its derivative would be times 3. Did I have a times 3 on this first term? No, and so I need to account for that by including what in my antiderivative? A 1/3. Then when I differentiate my antiderivative, 1/3 secant of 3x, I will get secant 3x times tangent 3x times 3 times 1/3, and I'll get the original. So I need to cancel out that missing, right, that missing derivative of the angle 3 with the 1/3 so that my derivative would produce the original squiggle underlying green. Let's keep going. Uh-oh. I'm going to interpret this as a power, right? This is a power rule. I know that negative 2 over x to the 5th is kind of like negative 2x to the negative 5 as I'm thinking about this in my head for a power rule. So I can reverse and undo my derivative power rule by adding 1 to the exponent and dividing by the new exponent. So I'm going to keep my constant multiplier, negative 2 out front, but I will go ahead and use my power rule for antiderivatives. That is, add 1 to the exponent and divide by the new exponent. So x to the, let's add 1 to the exponent. Negative 5 plus 1 would be negative 4. Divide by the new exponent would be dividing by negative 4. And then a constant integration of the negative. So let's go ahead and rewrite that so it looks better. So we've got 1/3 secant of 3x, and then negative 2 divided by negative 4 looks like a plus 1/2. And then x to the negative 4 on top is the same as x to the positive 4 on bottom. So I'm going to rewrite this as 1 over 2x to the positive 4th, and then plus c. And let's go ahead and check that, right? I want to see if this is correct. So how could I check to see if my antiderivative is correct? What could I do to check that? Riley?
You could differentiate.
Absolutely. We could differentiate our antiderivative and see if it produces the original integrand. So let's do a quick check. Ready? Constant multiplier 1/3 times. The derivative of the secant function is secant with the angle times tangent with the angle, then times the derivative of the angle. My angle is 3x. So times the derivative of the angle is times 3. Plus, pull out my 1/2. Do a power rule. My current exponent on the power, right? That 1 over x to the 4th is x to the negative 4. So its derivative would be exponent negative 4 times the base raised to the 1 less. The 1 less than negative 4 is negative 5 times the derivative of the base. The derivative of x is just 1. Let's go ahead and check. Ready? 1/3 times 3 is just 1 secant 3x, tangent 3x, and negative 4 times 1/2 is negative 2, and then x to the negative 5 is the same as 1 over x to the positive 5. So did it work? Yes, and I'm feeling confident about that. Awesome. Raise your hand if you had number 3 right. So number 3 was definitely a step up from 1 and 2. Okay, now comes the big bad mother daddy of them all. Yes, that's right. When we have two separate algebraic parts, we must determine which part is the derivative of the other, or a portion thereof, to determine the relationship between these two pieces, and maybe select, right, what I'm going to use for my u and my u substitution. So as I look at these problems, is x cubed the derivative of 2 plus x to the 4th, or is 2 plus x to the 4th the derivative of x cubed? Kobe?
X cubed is the derivative of 2 plus x to the 4th.
Absolutely, or at least part of it, right? And so when I'm going to choose my u, I want to choose u such that when I differentiate it, I spit out the other piece of my integrand function. So let's choose u to be quantity 2 plus x to the 4th. Then I'd be working towards, right? I'd be working towards an integral of root u, right? If we're letting u be that 2 plus x to the 4th, I'd be working towards an integral of root u. Then I know I can apply the power rule, just like we did in number 2. We add 1 to the, number 1, add 1 to the exponent, divide by the new exponent. However, I've also got these other pieces. I've got an x cubed and a dx, and I need to see exactly how those relate to du so that I can substitute in, right, complete my substitution, and then find an antiderivative with respect to u, because I have now u's as the independent variable in my integrand function. So let's go ahead and generate the relationship between du and dx by differentiating both sides with respect to x. If u equals 2 plus x to the 4th, then du dx equals, the derivative of 2 is 0 plus 4x cubed. Is that right? Multiplying over the dx to see how du and dx relate, I get du equals 4x cubed dx. And then which part did I need to complete my substitution? Well, I just needed the x cubed dx. Does everybody see that? I just needed to know what goes in for the blue underlined x cubed dx. And so what I want to do is isolate that blue underlined x cubed dx by dividing over the dividing over 4, so I get 1/4 du is what's going to go in to my original integrand for the x cubed dx. That's what's going to replace the x cubed dx and complete my substitution. So it looks like we had that whole thing. All right, I'll put my 1/4 here then. I'll put my du here then. since I can't move that, right? We've got our 1/4 du in for my x cubed dx. And now I'm ready to integrate. I'll kick this constant out front so I don't trip over it. A constant multiplier sticks around in differentiation, so it's going to stick around in integration as a constant multiplier. And now we'll apply what words? Well, we'll do power words. This is like u to the 1/2 currently. So I'll go ahead and integrate by adding 1 to the exponent. 1/2 plus 1 is 3/2, and then dividing by the new exponent. The new exponent dividing by 3/2 is the same as multiplying by 2/3, and then plus c. But our original integrated function had x's in it, so we should rewrite this with x's. It looks like we get 2 over 4 is 1/2 times 2, 1/6. Is that right? 1/6. U was 2 plus x to the 4th, all to the 3/2, and then plus c. I don't believe it. But Riley told us that Sammy.
Oh, I was wondering, why does the du disappear when you integrate?
That's a great question. Why does the du disappear when we integrate? Well, the du appears when we differentiate, right? When we differentiate, this u changed into the du dx. And we multiplied that dx over so that we could get a relationship between this dx and this du. At this stage, the du or the dx in the beginning is really just telling me the independent variable in my function is x. So when I find an antiderivative function, I should have blah, blah, blah x's in it. Here, it's telling me the independent variable in my expression has u's in it. And so when I find an antiderivative function, I should have u's in it, right? And then I'll go ahead and return back to my original x. So if I left this as a dx, I wouldn't be allowed to integrate this function with u's in it and have u's in my antiderivative. So this is with respect to what variable. You could treat it as 1 du, right? If you wanted to treat it as a 1, right? It's just the derivative of a u function is 1 du with respect to u. The derivative of a x function is 1. Derivative of x is 1 dx with respect to x. So we need the du to tell us the independent variable in my integrand. U substitution allows us to figure out that constant, right, algebraically, and so that's kind of why we use U substitution. But it's kind of like this showed up when you differentiate. Anna?
Somewhat like going from the 1/4 square root of du to the red one, what replaced the du? Is that the 2/3?
Right here?
Yeah.
No. So this du enables us to find an antiderivative and tells us there'll be u's in it.
Okay.
It says there'll be u's in this, right?
So actually because it becomes 1 because we're differentiating with respect to u.
Yes.
So the du just becomes 1.
Yes. I'm trying to think of a good way. When our y equals e to the x, right? Then my derivative dy dx equals what? E to the x, and my differential dy equals e to the x dx. If I told you that my differential dy equals e to the x dx, could you tell me what y equals? Yeah, you did with your differentials equations review with your partner last class, and you said an original function would have been y equals what? E to the x plus c, right? Well, how do we get there? We're going backwards. We're integrating, right? We're integrating, and we're going back and finding an antiderivative. What's an antiderivative with respect to y? 1y. What's an antiderivative with respect of e to the x with respect to x? E to the x plus c. Where did the dx go? Where did the dy go? Well, they showed up, right? They arrived. They showed up when we differentiated. So it kind of makes sense that they disappear when we integrate, when we go backwards. The same way that we undo the power words, right? When we undo the power words, we reverse that operation. We add 1 to the exponent and we divide it by the new exponent, just like we times by the old exponent and right? Times by the exponent, and then subtract 1 from the exponent. And so they show up when we differentiate, they disappear when we integrate, right? They're inverse processing. It's probably the best way that I can think about it. We actually need these in order to integrate. In order to have an integral symbol, we have to have the with respect to what variable. Otherwise, we don't know what's going to be in our equation. Awesome. Whew. Okay, so what do? We can box this. All right, we'll have more practice with antiderivatives. Paige.
For number 2, could
Yes.
you have e to the 2x instead of 2ex?
Great question. An exponential differentiates to the exponential itself times the derivative of the exponent times the natural log of the base. And so we couldn't have e to the 2x because when we differentiate it, then it would be e to the 2x. So because the current exponent is just x straight up, I know its antiderivative or derivative would just have the same exponent x. Kind of like, because my trig function differentiates to the trig function with the angle, right, times the angle, I know that I'm still going to have a 3x in there whether I'm going forward or backwards. Good. Other questions about that? All right, let's go ahead and take care of our OTL number 5 then. At this time, if you kindly take out your OTL number 5, give yourself credit for those that you out of 18, please, out of 18. And the related rate tax is included on that, right? 18. I know I did it. Yeah, thank you. You're welcome. Guys, related rates packet included, please. Pass the stapler. Please take a minute and make sure that your infinite canvas score is boxed nice and big on top. If you put the related rates packet on top, that's fine. Just make sure your infinite canvas score then is on top. If you put the bookwork on top, that's fine too. Final check with your name, first and last. Include the related rates packet, please, and then pass it back to the front. Front rowers, please make sure they're facing the same direction. I appreciate your help. Riley. 5 2 we're going to pass the next. Separately.
It's so weird. I think I had a little bit. Yeah. Got everyone. Oh, you're hilarious.
Everybody go with number 5?
Oh, yeah.
Okay, ladies and gentlemen, next I'd like to go ahead and collect your 5-2 activity differentials and linearization so that I can issue you stamps. And so once again, this is not a homework assignment, but it was going to take too long to issue stamps during class, and so I wanted to collect this separately and also give you a chance to complete it after we had our Bellwork discussion last class. So once again, 5-2 linearization and differentials. Make sure your name's on it. You don't have to give yourself any sort of score. Make sure your name's on it, and then we'll go ahead and pass them back to the front. You don't need to include the extra handout because it's not a stamp. So 5-2 activity, name, first and last, pass from the back to the front. Yeah.
Oh.
Thank you. Kobe, you're 5-2?
I don't.
Okay. 5-2. Thank you. Thank you. Thank you. Good. Thank you. 5-2. Everybody got it? Okay, ladies and gentlemen, thanks for your help. So, we have some antiderivative rules that we've already seen, okay? And so, we completed our power antidifferentiation by undoing our derivative shortcut words for a power function. I know the derivative of a power function, x to the n, is exponent times the base raised to 1 by x. So to get an antiderivative, we're going to undo those. We'll undo those, right, by reversing those operations. If the last thing we did was subtract 1 from the exponent, the first thing we'll do when going backwards is to add 1 to the exponent. If the first thing we did when differentiating was multiply the exponent times the base, the last thing we'll do when reversing that process then is to divide by that new exponent. So symbolically, the antiderivative of x to the n with respect to x is x to the n plus 1. Let's add 1 to the exponent and then divide by the new exponent. Right? So x to the n plus 1 and then divided by the new exponent n plus 1. Now, we're going to do a formal investigation of that 1 over x as an integrand function later. But for now, I included it because I want you to know this power rule falls short if trying to use it to anti-differentiate the expression 1 over x. How come? Well, what's the current exponent on that statement 1 over x? If I were to rewrite that as a power. X to the negative 1, right? And so if I were to try to apply the power rule to that, I would get x to the negative 1 plus 1 is 0, so I can add 1 to the exponent, and then divide by the new exponent. Well, dividing by the new exponent is dividing by 0, and that's undefined. And so I clearly cannot apply the power rule when anti-differentiating the expression 1 over x with respect to x. However, many of you already recognize an antiderivative for that, right? What would an antiderivative for 1 over x be? ln of x. The only thing that we need to include when going backwards that's different, right, is a domain issue. And so I want you to think about the graph of ln of x. Ln of x only occurs for positive input. So only over here on the right half of my xy coordinate plane. To the right of the y-axis is where ln of x exists. However, my original integrand function, where does that exist? Well, that's our hyperbola power function, right? Our hyperbola inverse power function. So we've got first quadrant, third quadrant. So we've got that function existing for both positive and negative inputs. It just doesn't exist at the very class until x equals 0. And so because the domain of my original integrand function, 1 over x, exists for both positive and negative, both halves of the coordinate plane, when I anti-differentiate and go back to ln, I have to include absolute value bars in my input so that now this graph exists for the left half and the right half. Still, both of them are undefined at x equals 0. And then when we go backwards, we want to make sure that we include a plus c. If it's an indefinite integral, that is no limits on the integral symbol, we want to make sure we include a plus c. All right, so we've got 2 antiderivative rules so far. You guys written down symbolically, you guys know all your trig ones, right? And so we've already used those and some exponential ones. But I wanted to point out the difference between that power function and the natural law. Awesome. All right, so today we're going to investigate the mean value theorem. A special application of the mean value theorem is called Rolle's theorem, and you guys saw this last year in pre-calculus and in FST pre-calc when you were working towards finding some maxes and mins. That's Rolle's theorem, and so what we're going to do today is develop the mean value theorem, which will be the last piece we need in the puzzle for the fundamental theorem of calculus. Dun dun dun! And so you hear fundamental theorem of calculus, and you might be thinking, wow, that sounds kind of like a big deal. And yes, it is a big deal. The fundamental theorem of calculus is going to make a connection between differentiation and anti-differentiation and form a bridge between indefinite integrals, right, antiderivatives that we were finding in the Bellwork, and definite integrals, right, the exact area underneath the curve. We're going to be able to evaluate definite integrals using antiderivatives, indefinite integrals, in accordance with the fundamental theorem of calculus, exactly and algebraically without the use of a calculator. We're going to be able to do that with the mean value theorem. I will provide the missing link that we need to connect indefinite to definite integrals. And so today's activity is a setup for next class. We're going to earn stamps twice in the activity, and so let's go ahead and mark those out. I need to add those. So you're going to get stamps in 3 places today. The first place for stamps is on your activity 5.5 at 6B. And then 10C. So that's in the actual packet. Everybody, if you want to identify those items in your 5.5 mean value theorem activity, 6B and 10C are the 2 stamps in the activity. Then, on the separate practice page, so on the MVT practice, number 1b. So that's the third stamp of the day. That's on a separate page. And then the final place I'll do is line 3 is part of your, probably won't get to until homework time, the definite integral practice number 8. That's your that's your fourth stamp. And that's vital that you complete that for the understanding of the fundamental theorem of calculus. And so we've got a separate stamp on a separate page from the previous two. We've got definite integral practice number 8. And it's vital that you complete that. That's why I added to a stamp instead of just including it as part of your regular OTL. You've got to complete that so that we can understand our fundamental theorem of calculus that we'll be developing next class. And so that's a super big day. All right, so 3 different places for stamps. We can go ahead and scoot into our cooperative learning groups. We'll come back together and check. And then I'll go ahead and record your OTLs and get you guys stamps for your 5-2 activity. Questions about what the next part of class is going to look like? Today we need a little bit more than 5 minutes for closure. So we're going to be aiming for about 23, okay, maybe 22, 23, 11, 22, 23, which is close to an hour, okay? Come back together because we've got a big closure today. Awesome. Go ahead and scoot in your groups. I'll pause the recording, and then we'll reconvene at about 20 after. Zoom now. Thank you, ladies and gentlemen. Let's go ahead and take a look at your closure from your note sheet today. What are the 2 requirements for the mean value theorem to apply to a given function f on the interval a to b? So we're looking for 2 requirements, and you can check with your partner quietly, but we've got 2 requirements. I'll be calling on you to share. Thank you, Brandon. Okay, so what are my 2 requirements in order for the mean value theorem to apply on an interval, right? Tess?
That it's continuous on a closed interval and differentiable.
Absolutely. Our function f has to be continuous on my closed interval a to b. And we've got to be differentiable, right? We've got to be differentiable on the open interval a to b. Awesome. So if I do have those requirements, thank you, Tess. If f is continuous on a to b and differentiable on a to b, then the mean value theorem states, algebraically, there must be some x equals c on my interval a to b such that f prime of c, the slope of the tangent line, right, to the curve, is equal to f at b minus f at a all over b minus a, the slope of the secant line connecting the endpoint. So algebraically, let's go ahead and write that. So algebraically, there exists an x equals c with c in between a and b such that f prime of c is equal to f of b minus f of a all over b minus a. I'm going to do that. Bless you. Graphically, let's see if we can't construct a visual representation for the mean value theorem. F prime of c represents what about a function? Well, first we need our function to be continuous and differentiable over an interval. So f of b minus f at a all over b minus a, right? Graphically, what is the right side of this equation? What does this right side of this equation represent graphically? What's this talking about? Kobe?
The slope of the secant line.
Absolutely, and so the slope of the secant line would be that red part of the equation, right? There's my slope of the secant line. And what does f prime of c represent graphically? What does f prime of c represent graphically? Brandon?
The tangent line to a point that's parallel to the secant line?
Absolutely. So guys, if we visually estimate where that would occur, it appears as though the tangent line to the curve, right, we want that to be the same as the slope of the secant line to the curve. And it looks like that happens right around there. So here's C, here's A, and here's B. So we've generated a graphical representation of the mean value theorem. One, we need our smooth, continuous and differentiable function on the interval A to B. Then we're guaranteed to have some x value between A and B, call it x equals C, where the slope of the tangent line, that's f prime of C, is equal to the slope of the secant line in red, right? That's the f of B minus f of A all over B minus A. And we're totally going to get there. How is Rolle's theorem a special case? The special case is the endpoints are just equal. So the endpoints f at A and f at B, the endpoint y values are equal. So it's just a special case because they're still continuous and differentiable. Ooh. And we can complete that if f is continuous on A to B and differentiable on A to B. And what's our last part? Well, we just added that the y values, the y coordinates of the endpoints are equal. Then what must be true? Well, there has to be some x equals C with C on my interval A to B such that. And what was the special case with Rolle's theorem then, Jake?
You'd say horizontal tangent.
Absolutely. So how can we say that was primes? Absolutely. Way to go, you guys. I apologize we went long, but that's exactly right. And you've got your mean value theorem for next time. Well, set up the fundamental theorem. Great work. I'll stop the recording and save it.